instantaneous speed. This is the average speed, but when we do derivatives, we get instantaneous speed. Okay, that's the idea. And then, if I take what does acceleration mean? What does the word acceleration mean? How fast the speed is changing, right? Right? When you say I'm accelerating, you press down the accelerator, what are you saying? You're saying my speed is increasing, right? So that's the change in the speed over time, right? The change in the speed over time. But in calculus, this becomes d. So we get d speed dt. But what is speed? We just said that speed is this, right? So instead of d speed, I have what? Becomes what? d dt. What goes here? Not speed. I can write this. ds dt. But what's that? That's the second derivative. Right? That's the second derivative. So the acceleration is the second derivative of s. The speed is the first derivative. The speed is the first derivative, right? We said the speed was the first derivative. This is the first derivative here. It's basically this is the speed. And the second derivative is the acceleration. Okay? So again, to repeat this again, when we have this kind of formula, distance, this is not speed, this is distance, S stands for distance. Distance as a function of time, the first derivative of that gives you the speed. Right? It's only in the case where you have a function that gives you distance in terms of time. In that case, the first derivative gives you the speed of the object, and the second derivative gives you the acceleration of the object. Okay? So, here's the question now. So it says the position s of a point is given as a function of time. So s is a function of time. And then find the acceleration. So how do you do that? Just find the second derivative of this, right? And that gives you the acceleration. So what is that? That's not too hard to do. This becomes 0. The first derivative of this is 1, but the second derivative of this is 0. Right? And then this one becomes what? Minus 32t is the first derivative. So minus 32. So the answer is minus 32 here. Okay? So what's the acceleration? Minus 32. So this is like a rock falling, because it's negative. So it probably means it's, it could be a rock falling, I mean. Okay? So what's the answer? Minus 32. Does the answer have a t in it? No. What's the answer again? Minus 32. There's no t there, right? What does that mean? It means the acceleration doesn't depend on t. There's no t in there. So if it doesn't depend on t, it means it doesn't depend on time. It means it's always minus 32. So we call that constant acceleration. Okay? That's called constant acceleration. Okay? And then they ask part B, what's the acceleration at this particular time? What time? When t equals 6. But I just asked you, does the acceleration depend on the time? You just said no, it's constant acceleration. It's always minus 32. It doesn't matter if it's 6 or 10 or 50, it's always, there's no t in the formula. So it's always 32, minus 32. So it doesn't matter that there's a 6 there. It's still minus 32 here. Okay? Okay, so that's one physics example. I tried to stay away from physics examples, but I guess it's probably good to have that one example. Actually, one reason why it's good to have that is because all of calculus came from trying to do this kind of problem originally, 350 years ago. Because that's where it came from, so it probably works very well for this kind of problem. Okay. Should we try something else? Let's see, is there anything on the internet? Let's see, here's something about inflection points. Inflection point. Let's see if we can find a video. Let's find. Let's see what Khan Sensei says about inflection points.
If you were paying close attention in the last video, an interesting question might have popped up in your brain. We've talked about the intervals over which the function is concave downwards, and then we talked about the interval over which the function is concave upwards. But we see here that there's a point at which we try...
Okay, now last week, we discussed concavity. And concavity had to do with like whether if you pour water into something that's concave up, we say that the water won't spill out. You pour water into here, it holds the water, whereas when it's concave down like this, if you pour water on it, it's going to spill off, right? So that's one way to remember what we mean by concave down, the red one, and concave up, the other one. Now, last time we showed a particular property that will tell you the concavity. Can anybody remember that? It was the second derivative. Second derivative tells you the concavity. Okay, but I guess he does that before this video. But now he's focusing on this point right here. So it's concave down here, and actually I mentioned this last week. But it's concave down here and concave up here, and he's focusing right on that point.
Transition from being concave downwards to concave upwards. Before that point, the slope was decreasing, and then the slope starts increasing.
What does he mean by that? What's happening to the slope as we move along the red? Is the slope positive or negative here? Right here. Positive or negative? Here's the slope. Is that positive or negative? That's positive. How about over here? Is the slope positive or negative? Negative. So the slope is going from positive to being 0 to being negative. We call that decreasing. When something goes from positive to negative, we say it's decreasing. So the slope is decreasing as we move from the left to the right. However, what happens over here? Now it's negative, then it's 0, then it's positive. So now what's happening? Something that's going from negative to positive is increasing. So we'd say the slope is increasing. So in the red one, when it's concave down, the slope is decreasing, but when it's concave up, the slope is increasing, right? So how about right here?
And then the slope started increasing. So that's one way to look at it. Right here in our function, we go from being concave downwards to concave upwards.
Now what is this horrible, I hate this picture, but what is the relationship between this picture and this picture? Well, here's the answer right there. What is this function? Can you read that? It says f prime there. This is f, this is f prime. I'm not sure why we have to draw these pictures. To me, they always confuse me, but you see them a lot in these books. So I guess we have to look at it. So here's f, and here's f prime. So so they're saying if this function looked like this, then the graph of its derivative looks like that. So what does that mean? Well, what about this point right here? What's the height of that point? 0, right? It's crossing the x-axis, so it's 0, right? But this is not f. This is what? F prime. So it means f prime is 0 right here, right? Is that true or false? F prime is 0 right here. Well, it means we're talking about f prime when this is f. So what is the derivative right here? It's flat, right? So the derivative is 0. That's why they put this crossing the x-axis here. Okay, I really don't like these, but that's what they do. How about right here? Why does this cross the x-axis? It means the derivative is 0 here. Is that true? Yeah, it's flat here. Okay, so this is a picture of the derivative. So, as I said, they do that a lot. Now look what he does. He even makes it worse. He goes one more step. What's this? This is the second derivative. It looks like this. Is it true? That means the derivative of this. So this is flat right here, right? That means the second derivative should do what? Should be 0 there. Okay, I really don't find these pictures to be insightful at all. They don't help me to understand anything. But anyway, that's what he's doing here. Okay, but going back to the original question, which is about inflection points. So this point is called an inflection point. Let's see what he says.
When you look at our derivative at that point, our derivative went from decreasing to increasing. And when you look at our second derivative at that point, it went from being negative to positive. So this must have some type of a special name, you're probably thinking, and you would be thinking correctly. This point at which we transition from being concave downwards to concave upwards, or the point at which our derivative has an extremum point, or the point at which our second derivative switches signs like this, we call it an inflection point. Inflection point. And the most typical way that people think about how could you test for an inflection point, it's a point, well, conceptually, it's where you go from being a downward opening U to an upward opening U, or when you go from being concave downwards to concave upwards. But the easiest test is it's a point at which your second derivative switches signs. So in this case, we went from negative to positive, but we could have also switched from being positive to negative. So inflection point, your second derivative, f prime prime of x, switches signs, goes from being positive to negative or negative to positive, switches signs. So this is a case where we went from concave downwards to concave upwards. If we went from concave upwards to concave downwards like that, then this inflection point, at this inflection point, up until that point, the slope was increasing, so the second derivative would be positive, and then the slope is decreasing. The derivative is decreasing, so your second derivative would be negative. So here your second derivative is going from positive to negative. Here your second derivative is going from negative to positive. In either case, you are talking about an inflection point.
Okay, so do you understand what's meant by an inflection point? So an inflection point is when the concavity changes. So what is the concavity in this area here? Here. Is it up or down? Concavity is down here. What is the concavity in this area here? It's up, concave up. So somehow it must have changed. Somewhere it must have changed. The question is, where does it change concavity? So in this picture, we would guess that it changes right here, right? So what is the coordinates of that point? Who knows? Oh, here, 2 and 2, okay. So what are the coordinates of this point? -2, 2. Right, the coordinates of this point right here. This point is where it changes inflection. Sorry, wrong. This point is where it changes concavity. That's called an inflection point. The concavity is down here. It's called down concavity. The concavity is up here. So somewhere it must have changed from being concave down to being concave up, and it's obviously this point here. And what are the coordinates of this point? -2, 2. So the inflection point is -2, 2. All right, that makes sense? Okay. Same thing here, they ask you where are the inflection points. So here's one, and here's another. So it's concave up, then it switches, concave down, then it switches, concave up. Okay. A lot of homework. Okay, let's see what other homework we have. Let's look at this one. Okay, last time, just to remind you, we talked about, I think, 5 special words relating to maximums and minimums. So can you remember those words? Can you remember one of those words? Five special words. 5 vocabulary words you need to remember. Can anybody tell me one of them about maximums and minimums? So like we had a function that looked like this. Something like that. And we wanted to talk about the maximums and minimums. So like here, 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 and maybe here. So there were 5 vocabulary words that we talked about. Can you tell me one word? 1 out of 5. What is it? In here. What?
Stationary.
Okay, stationary point, that was one word. Good. Now, I forget. Is it AR or what? Stationary or stationary? AR1, okay. Right, I guess the E1 is paper, right? Okay, stationary point, that's right, good. Okay. So I'm happy, even we got one. But I'll shoot for another one. Anybody give me another one?
Stable.
What?
Stable.
Oh, right. What was it?
Stable point.
Did we have that word? Stable? I think that is one of the words, but I don't think we did that one actually. Stable. I don't think we did say that. But that is a word that's used in this context. But anyway, another one.